like to invite all of the panel speakers and also the plenary speaker if still there. So excellent introduction. So I'm very, very excited to have you all here in this session together because especially, there are lots of different variations of talks. Some of them talk explicitly about brains. Some of you talk explicitly about no brain, the mechanical intelligence, in other words. And the case in point is the Cole's mechanical intelligence in feet, and the autonomous embodied intelligence in plants. But on the other hand, we have all this very fascinating research by Kenji about the brain modeling, Aoki's spinal cord modeling, and then Tetsuya and the Cosimos, how to mimic the function of brains and the nervous systems. So I think this is my first question to all the panelists over here. What's your position, brain or no brain? Or how do we think about brain as in the context of embodied intelligence? The good thing is that the embodied intelligence is coming kind of common theme for all of you, regardless of your opinion about brain and brain functions and roles. I'd like to have a bit of feedback. What do you think the role of brain, what the brain is doing in the context of embodied intelligence? I don't know, is there anyone who wants to start your opinions? Otherwise, yeah, okay, you go ahead.
Well, I think for me, brains are interesting additions to the spinal cord, useful to some extent. No, I'm a bit provocative here. No, but for me, I see the nervous system as really multi-layered, where you have multiple redundant systems, and even when we do locomotion, we can do cortical locomotion, as I would call, so really dance-like locomotion or strange-like locomotion, or we can be more spinal cord-driven locomotion, and I think that's the beauty is any motor movement we do can be done in different ways with a multi-layered control, and that's also the challenge, by the way, to decode, because there are so many things that are, I think we underestimate, like the midbrain and the hindbrain. The brainstem, there are many things happening there that we underestimate that are hard to measure. And I see really behavior as multi-layered behavior, let's say, and very interesting interaction between all these.
Anyone else have a... Yeah, Thomas, you go ahead.
Yeah, so I'm a bit out of the brain discussion because I think plants definitely have no brain, but they do not need necessarily a brain. So I'm totally with Åke that there is many things for which you don't need a brain. And in plants, there is another aspect because we have in plants, I would say, two types of interaction with the environment. One, which is called responsiveness, which means a direct interaction with the environment, which is often in plants passive, and then acclimatization, which goes over a longer period. And the question is, do we need for embodied intelligence some decision-making in a way how we quote a decision? I think for plant, a decision is, for example, to bend away out of the wind. But this is a passive decision. The plant doesn't say, oh, great, there is a wind coming, I have to bend down. And I think this is, for us in plant science, also for soft robotics collaborating, often a hindrance because the terminology is very, as I said, for plants, it's very complicated to use the well-established kind of definitions.
Okay, Tetsuya, you want to go next?
Okay. Yeah, actually, it's very difficult question. So now actually brain seems to have many different types of functions. But I think one of the important things is now prediction. So because so as you mentioned, they are layered systems, and of course, in the first way, the intelligence comes from the body. So maybe it's a common knowledge. But now maybe so the layered could be handled more. So maybe the different time scale, different size and dimensions. So it could be generate kind of the representation to predict to adapt to the environment. So that is one of the big and important functions. So so ultimately, so that the representation connect to the symbolic representations maybe. So First is so such kind of layered, and also the maybe is top-down prediction and bottom-up. So then there's kind of the conflict and the interaction. That kind of makes some intelligent behaviors. That's I think one of the important functions in the brain.
Okay, thank you, Tetsuya. Any other point? Cosimo, do you want to add?
Yeah. So I mean, I completely agree with all the other points that's been mentioned. I maybe to add even more what Oke said, it's to be even more extreme, all the neural activities can be seen as a nice addition to the mechanical intelligence, included the spinal cord, right? Because this is what we have seen more and more with robots, and it's definitely at least clear for animals. So yeah, I think already some astonishment while looking at animals and seeing how their mechanical structure already solve like 80% of the problem quite often. Not 100% because you still need that bit of neural activity on top, which at least for simple motor action comes often with low-level circuitry. But yes.
Okay, thank you, Cosimo. Okay, yes, go ahead.
No, just to complement what Tetsuya was saying is indeed, I think the brain is a key part of anticipation and predicting and having internal imagery and being able to plan. So without the brain, you cannot do much, but just to be on the other side. And I think that's the beauty is when I go jogging, I'm always impressed by how my brain is able to predict where my foot will be in 5 meters or so and able to adjust my locomotion. So having this internal model of the world, being able to predict and adjust what's going on with the spinal cord is a key part. And I think Kenji also gave a wonderful talk to see how this exploration in the head is important before even planning the action and doing the action.
Okay, so Cole, you want to go next?
Right. Maybe I like to mention about from a very different perspective. Maybe most of us are talking about the oscillatory movement is completely related to the embodiment in this session, right? So for plants, for the oscillatory movement of the robot and me, locomotion, and Aoke also the locomotion of the salamander, everything is related to the oscillation. And actually this kind of oscillation is very generating a feed for a tone, so that they will decrease the calculation, means that the function of the brain. So I think that the brain and this the environment would be complementary to some extent, especially talking about this dynamic stuff, I think.
Okay, thank you.
Maybe related. Yes, it's very important point for the even so generating some complex tasks. In my case, not so complex, but upholding task. And it's very important to encode such kind of motion is some cyclic attractors. So then you see then so the robot keeping folding, and such kind of oscillated motion, kind of cyclic motion is to the very stable embedded in such recurrent neural networks and deep learning models. Maybe then such comes from the body oscillations originally. So that's my impression here. Yeah, sorry, that's my comment.
Okay. Yeah, and today in my talk, I mostly talked about rather new part of the nervous system. I resonate with Oke about the importance of link between the spinal cord, midbrain, and also the more recent brain part. And also, I also concur with Cosimo that we can utilize some kind of attractor or manifold structure in the physical system that will greatly simplify the problem. But how our brain can kind of almost automatically find such important manifold or like a attractor. So yeah, that is something I really want to find out in my future research. Yeah.
I have a specific question to Kenji, but you mentioned about the new part of brain and the old part of brain. I think this is a really interesting discussion, actually. So your research more focusing on new part of the brain these days. So, how do you think of all this? The history of a new part of brain evolved from old part? Like, is there any explanation how we can talk about all these parts in a coherent manner?
Yeah, so then the evolutionarily newer part, like neocortex, would like complement all the existing mechanisms. And so the cortical processing would be very much depending on the subcortical processing. So, but they give you some more like flexibility and also more advanced predictive mechanisms, right? Yeah. So probably if you have a cortex alone, your brain have a hard time actually working in this complex environment, right?
I've got, by the way, I've got an interesting question on a chat. And the question was if plants can do predictions, and this is a really intriguing question. I say plants have a kind of, let me say, mechanic memory sometimes, so they can be trained. And again, the question is, can this be called a prediction? I just don't know. But it's really interesting because I think prediction is something also which is very closely linked to intelligence. And yeah, thank you for the question.
Absolutely. This was actually another question I wanted to ask to Thomas and Ko at the same time, that brain is usually regarded as the predicting machine, learning machine, but actually without brains, you can also do prediction and decision making at the same in many cases in nature. So Ko, I don't know whether you have any comments about whether your mechanical intelligent machine, the legs, can do the predictions or decision making by itself. In some ways, I think it depends on how you define them. But I'm sure you have thought of this kind of aspects in your mechanical intelligence.
That's a kind of difficult question, I think. But I think that the prediction is a kind of a very subjective word, because if you assume that you don't have beforehand, then there's something will be something you think will be the prediction, right? So it's a little bit difficult whether the mechanical structure will generate physically prediction or not, because the physical mechanics is not really subjective.
That's a really good comment. We're stepping into the philosophical questions now, right? What does it mean, prediction in the first place? And I think that's a very important discussion. Tetsuya, go ahead.
Yes, sorry, just one comment. Yes, the sense of mechanical dynamics is body and environment seems to entrainment coupling. And in my experiment, it's also just a coupling of neural networks and the body and the environment. So actually, it's including the sensors, visions, and motions. So what I called it a prediction. But just actually, it's a result of the entrainment of such a body and recurrent neural networks. So I say that it always generate a fake image, so expected image in the future, and that's a result of the entrainment. So by me, I think so. It's deal with almost same phenomena. So very similar phenomena actually. So body levels, and okay, mentioned, so they are layered. So just we can grasp such a different levels and dynamics in the same way, I think.
Okay, anyone else have a feedback? Okay, so I think we can also invite some audience to speak out, some questions or discussion if you have. So please raise your hand, and then probably we can unmute your comments. So one of the things I also like to discuss with all of you is a bit of a theoretical aspects of this interesting discussion, because there are lots of interesting cases and in nature and also robotics, and we are talking about very similar thing, but we probably need to have a theoretical foundation how we should, what's the good theory behind all these ideas of decision making, predictions, or learning. Of course, we have a reinforcement learning. We have what is it called? The eigenmanifold of the behaviors. That's also a very interesting theoretical foundation to explain some of our intelligent behavior, embodied intelligent behaviors. Maybe I just like to start with the Cosimo, how you think or view about how we should approach this kind of theoretical problems.
Okay, that's quite a big questions. What we are trying to do is to start from like a very extreme point of view, which is try to look at how much intelligence can the body give, and so kind of trying to formalize what this means for the specific task of periodic oscillations. Because why looking at periodic oscillations? I mean, first of all, because it's easier theoretically. That's the first reason, and the other is because since we are so focused on the mechanics, as we were discussing before, I think it's the task of the mechanics to deal of those tasks in which you don't need to change a lot. So you need to be very have a big repetition. So maybe there is some kind of spectrum that should be defined theoretically or more precisely of which kind of some kind of a spectrum of how much the task is repetitive, how much it requires adaptation, and this would probably make clear which level this should be tackled.
Right. Yeah, thank you. Anyone else have any opinions?
Maybe a bit I think more relate to understand natural intelligence, embodied intelligence, or let's say the mammalian nervous system. I think a key thing we have to do is look at in which spaces are signals sent, and in which space do we do planning and learning. So for me, I'm always impressed by how the nervous system handles high dimensional data. So our retina and everything is high dimensional, and then condenses everything in the optical nerve, so there it's much more compact. And then again, you have a big explosion of dimension in the cortex, and then the descending pathways that go to the spinal cord are really a subset of signals. So there you have again a reduction of dimensions, and I think it's important from a theoretical point of view to be aware of that. And also, especially for learning motor control, is to be aware that this space going from high part of the brain to the spinal cord is a very non-uniform space and a very strange space. So it's not in joint angle space, it's not in muscles, it's in signals sent to the spinal cord. And sometimes you activate a rhythmic circuit, sometimes you inhibit a reflex. So the motor learning has to be handling with a subset of strings. I like to see the spinal cord as a puppet on strings. So you're playing with some strings. But these strings have very strange behavior. So I think we, at least from a theoretical point of view, a key thing is to know what are the strings basically and what do they do. And I think that's very important for understanding natural behavior. It's maybe less important for creating an artificial system that has embodied intelligence, but for sure for, let's say, computational neuroscience, I think it's a key aspect.
That's interesting views, and am I understanding right, okay, that you're suggesting that we probably have a very high dimensional system in the brain and a very high dimensional system in body, but then in the middle we have a lower communication bandwidth, You think is this a good model to discuss, or is this?
Yeah, exactly. I think like in the visual system or in any sensory system, we have filters. So we have high dimensional inputs with low dimensional outputs. In the spinal cord, we have pattern generators, low dimensional inputs, complex outputs. So indeed, at some point, in several key places in the brain, maybe Kenji can correct me, but we really have a very big change of dimensionality, and I think we have to. That's a key part of what the brain is doing, and I think that's why also the spinal cord is so important, because it's probably there to. If the motor cortex has to learn in muscle fiber space, we have millions of muscle fibers. We would never be able to learn. It will be too high dimensional. So being low dimensional in some places helps, and I think the pattern generator for sure helps at the spinal cord level.
So, okay, what is the idea? Is that for the economy of wiring, or the low dimension representation actually helps better performance?
Yeah, I think both. I think we have a bottleneck. So the number of axons going through the cortical to spinal cord tracks, they are limited. So we have subset and it's limited. So I think functionally it had to be limited, and then it was let's say from a physiological point it had to be limited. And I think functionally it's interesting and it makes sense to be lower dimensional. To not overwhelm learning in a too high dimensional space.
Yeah. So how such a good low dimension code can be found? That is a really fascinating question. Yeah.
Mm-hmm. Yeah.
But yeah, then I think the question is why we evolved to have so many degrees of freedom in the body. Because if it's just a matter of reducing computational complexity, as an engineer, the simpler solution would be just have low dimensionality on the mechanical side.
That's a good point. I would answer. We have to do so many things to survive. So not only locomotion, only it's a small part. We have to feed. We have to groom. Like removing parasites is almost as important to locomote. So the degrees of freedom to remove your parasites are probably as important as those for locomotion. And I think we need these degrees of freedom for survival. An animal would have too few, would probably die, I think. So I'm curious to hear, maybe Ko, you are more into the biomechanics. Would you agree with that? You need many degrees of freedom to survive.
Yes. Redundancy is the key for the adaptability. So basically, to survive, the redundancy is a very key. We need a lot of degrees of freedom.
Mm-hmm.
Physically, I must say that in the sense of the embodiment, we have to have a bunch of degrees of freedom so that it can, some part, even if some part is collapsed, then the other part will compensate. So, of course.
Mm-hmm.
But I think it's also very interesting in the work of your work, that in a sense, all this, some of these degrees of freedom are directly resolved on a physical side. So you add them, but also from the computational point of view, neural point of view, you already remove them physically. So you get the benefit without the burden of having to manage them.
Yeah, right. And also what I like to emphasize is that it is not just one mechanism, but the many, I told that the bones we have the 26 bones, which has so many degrees of freedom in foot. So which means that not only few number of function can be utilized, but many. So and based on based on the change of the terrain, for example, maybe some of the function will increase and some of the function will be depressed, but dynamically it will change the coordination in between by physical interaction. And actually, the brain, I think that the brain will coordinate to some extent of the combination of the behaviors of the bones. Maybe I should not say, I should not use the coordinate word, but instead maybe, how can I say that? The, like a hormone. I mean, to, how can I explain that? It's not really controlled, but basically it's a distributed dynamics, but some of the connection will be modified by the brain, I think.
Mm-hmm.
Well, this is a really interesting discussion because, of course, in nature, there are simpler animals and more complex animals. And, the complexity is not only solutions for survival, but on the other hand, if we want to understand ourselves, humans, the complexity is the key. Like why we're so complex, how our brain evolves in a complex way. And I just want to go deeper into this discussion. I think, especially asking the question to Kenji about the recent development in the brain science and neuroscience about, the brain science have been progressing with the idea of the curse of dimensionality and reduction, the dimensionality reduction, and Nicholas Bernstein problems, how we control so many muscles at the same time in timely manner. What's your views on today's research about the dimensionality problem? Can you give us a bit of your perspective about this problem?
Yeah. So on the sensory side, there has been a lot of work of a feature detection and also the unsupervised learning to capture some kind of a low dimension latent structure in the very high dimension sensory observation, right? So, but the motor side, so the research is not so advanced compared to the sensory side, because in the sensory case, you take a lot of data and then put it into a learning algorithm and see what happens. But on the motor side, you have to create your own output while moving, right? So then what kind of a coding is needed depends on what you are going to do, right? So I don't have a good idea yet. And then so what is the principle and mechanism for creating like a necessary and sufficient low dimension representation for the motor purpose? That is something we have to study very hard.
Excellent. Yeah, I think that is a very nice summary of where we are, and probably that's related to what Aoki is trying to do with action coding through spinal code and the learning of action with all the Cosimo and Tetsuya trying to do. Yeah, that's absolutely a great idea. So any other questions? And if not, I just want to summarize this session by asking this question. Oh, there's one question from audience. David Thorvaldsen, do you want to turn on your microphone and ask us a question?
Yeah, I would love to, if I could. Thank you for the conference so far. Very interesting and interdisciplinary, it seems like. Seems like there's a lot of fields touching upon this subject of embodied intelligence. And so I just had a question relating to one of those things I thought it seemed like intersected many of your fields, which is the oscillators. This is something I'm studying in my master's thesis now, where I'm modeling musical robots as oscillators, where they are supposed to synchronize to each other by also also seeing if computational self-awareness can increase this capabilities of synchronizing oscillators. And so I just wondered what you kind of think these oscillators capture, since they seem to be so like omnipresent in many of your fields. Like what about intelligence and brains, for example, do oscillators capture?
Yeah, okay, you can probably go ahead.
Yeah, if there are oscillators, I'm always happy to talk about oscillators. When you think about it, life without oscillation could not exist. So our heartbeat, our breathing, the sun going round, so everything is oscillation. So it's really a key part. And for me, I see locomotion indeed as a beautiful coupling between a mechanical oscillator, the pendulum, like Cosimo also showed, and the neural oscillators. So many things are indeed related to oscillations. And then at the same time, we are rarely in steady state. So animals are able to always activate or deactivate oscillations, do discrete movements, do all kind of things. So being able to do this switching and not staying too much periodic is also important. So I think that's the beauty, is we able to switch or superimpose periodic and discrete movement. And also maybe something we haven't thought, well, we should maybe discuss is being quasi-periodic or chaotic. Indeed, like what Kenji said, when we do locomotion, we also have to do exploration. So we don't have to repeat always what we do, not only exploit, but exploration is also good, because otherwise you never improve, or maybe you stay stuck. So I think that's the beauty as well, is oscillator can easily become chaotic, and then you start exploring. So it's a good building block, and adding discrete pattern generates, then you have really, I think you cover most of motor control.
Excellent, thank you. Well, thank you for all the panelists joining this session today. So I think this was an excellent opening of this conference. Like embodied intelligence actually covers many different disciplines, and let people think in a collaborative way about really fundamental questions. And we already have picked up some fundamental keywords, the questions such as brain versus no brain, complexity, dimensionality reduction, prediction, and the decision making, and so on and so forth. And I think this is an excellent opening of this conference, and we're going to continue with discussion in the next 2.5 days. So I think I would like to thank all the panel speakers and the primary speaker for wonderful contribution, the first session of this conference. Yeah, I just have to approve for now. Thank you very much. So the next part of this conference is actually a breakout session. Many of these panel members are going to show up in the breakout room so that we can continue with this interesting discussions. But we have also assigned talks. Like we have 2 rooms, room 1 and room 2. Each of them has 7 speakers. If you have additional time, you can do continue with the discussion in the breakout sessions. Afterwards, we will have the main room open again at 1 p.m. GMT to start the afternoon session. So I hope you enjoy the breakout session with a smaller group discussions. We will see you again at 1 p.m. later. Okay, so just remind you that you need to push the interface, Zoom interface of breakout rooms, and you can probably move to your rooms of your choice. Thank you very much once again, and we'll see you later again. If you have any problem moving to breakout rooms, please remain here and put it in the chat or put it in Discord, and we will help you. Thank you very much. This is the end of the morning session. Thank you.